the previous lecture, we discussed in detail about free vibrations of single degree of freedom systems. We discussed what are damped and undamped free vibration systems, how to model the mathematical equations for such type of systems, what are the methods involved while developing the equations of motions for such systems, how Newton's second law of motion is used to develop the equations of motions. Then we discussed the concept of damping ratio zeta and critical damping constant. We also discussed how the value of zeta, that is damping ratio, affects the performance or response of a practical free damped vibration system. Then we discussed about the concept of logarithmic decrement, how it is practically related to physical vibration analysis, and how can we use the data from vibration sensors in order to determine the damping ratio of a free damped system. So in this video lecture, we will start covering some numerical problems which are related to the theory topics which we covered in the last video lecture. So let's get started. The first problem is related to a spring damper system, and we are required to derive the equation of motion for this system. As the figure shows, a rigid bar which is pivoted at point O has two springs and a damper which are attached on its either side. The distance at which the springs and the damper are attached to the bar are given. Since the bar is pivoted at point O, therefore it can only rotate clockwise or counterclockwise about its pivot point, but it cannot move across it. Therefore, if the bar rotates clockwise about point O as shown in figure, a deflection diagram is made to show the deflection of the bar at different points. As it can be seen from the deflection diagram, that on the right hand side there is a spring having stiffness K. So the deflection on this side may be called as x1, while on the left hand side the spring has a stiffness equal to 3 times K. Therefore, we may call the deflection on that side as x3. Also, a damper is attached to the bar on the right hand side at a distance L by 4 from the pivot point. Therefore, its deflection may be called as x2. Since the rotation of the bar is constrained by a spring damper system, therefore a small amount of deflection is produced in the bar, and for small deflections the arc made by the bar is approximately straight. Therefore, we may write the similar triangle ratios by using the arc length formula, that is S is equal to r theta, as follows. X1 is equal to L by 2 plus L by 4 into theta. X2 is equal to L by 4 into theta. Since X2 corresponds to the arc length made by the damper and the work done by the damper involves the derivative of displacement, that is, it involves velocity. Therefore, we may take the derivative of x2, which becomes x2 dot is equal to L by 4 into theta dot. Then we have x3 is equal to L by 4 into theta. In the next step, a free body diagram is drawn to show the effect of forces on the bar. Then We apply Newton's second law of motion on this system. Since the bar has rotational motion, therefore Newton's second law can be written as follows. Summation T naught is equal to J naught theta double dot. So for counterclockwise moments, the above equation can be written as follows. Minus Fs1 into L by 2 plus L by 4 minus Fd into L by 4 minus Fs2 into L by 4 is equal to J naught theta double dot. This is called as equation 1, where Fs1 is the spring 1, Fs2 is the spring 2, and Fd is the force applied by the damper. As it is evident from the deflection diagram and free body diagram that Fs1 is equal to k into 3 by 4 L theta, or Fs1 is equal to 3k L theta upon 4 is equal to kx1. Fd is equal to cx2 dot is equal to c by 4 into L theta dot, and Fs2 is equal to 3 by 4 into KL theta, or Fs2 is equal to 3kx3. Now, after substituting these values in equation 1 and simplification process, we get the final equation of motion as follows. J naught theta double dot plus CL square theta dot upon 16 plus 3KL square theta upon 4 is equal to 0, where J naught is the polar moment of inertia of the rod about point O. We can also find out the natural frequency of this system by using its equation of motion as follows. As we studied in the start of this chapter, that the frequency of a single degree of freedom system having damped or undamped oscillation is given by under root k upon m. That means the frequency of a single degree of freedom system entirely depends upon the stiffness and inertial elements. And in order to find out the natural frequency of such a single degree of freedom system, all we have to required is to substitute the value of the system stiffness and its inertial element, which may be find out from the equation of motion of the given system. Therefore, for this given problem, the coefficients of the stiffness are 3kl square upon 4 and j naught, and by substituting these values in the formula of natural frequency, we get omega n is equal to under root 3kl square upon 4j naught, or in short we can say that the natural frequency of a single degree of freedom system is equal to under root coefficient of theta upon coefficient of theta double dot if the system is performing the rotational motion, or omega n is equal to under root coefficient of x divided by coefficient of x double dot if the system is performing linear motion. Or in another words, we can say that omega n is equal to under root coefficient of the stiffness element divided by coefficient of the inertial element. So that's the end of the first problem related to equation of motion. We have another problem related to such type, and it is given as follows. The problem states that for the structure shown in the figure, find the equation of motion and damped frequency in terms of mass, stiffness, and damping of the system. As shown in the figure, the rigid bar is pivoted at its one end at point O. A spring is attached at a distance A from point O, while a viscous damper is attached to the other end of the bar at a distance L, which is measured from the other free end of the bar to the pivot point O. So before moving towards the formulation of equation of motion for this system, let us consider the moment of inertia of the rigid bar about point O. Since we know that for a rigid bar, the moment of inertia or the polar moment of inertia, that is J, is given by 1 upon 3 ml square. Then by applying Newton's second law of motion, we can write the form as follows: summation T is equal to J naught theta double dot, or minus Fs into A minus Fd into L is equal to J naught theta double dot. This may be called as equation 1. Since from the given figure and the deflection diagram, it is clear that Fs is equal to Kx1 and Fd is equal to Cx2 dot. And for small angular displacement theta, x1 is approximately equal to a theta and x2 is approximately equal to l theta, which implies that x2 dot is equal to l theta dot. Here we take the derivative of x2 because it is the arc distance covered by the viscous damper C, and for viscous damper we always show its work done, and its work done is equal to Cx dot into x. Now substituting these values in equation 1, we get minus Ka square theta minus Cl square theta dot is equal to J naught theta double dot. And after simplification process, the equation of motion becomes J naught theta double dot plus Cl square theta dot plus Ka square theta is equal to 0. Please note that in this final equation of motion, the term Cl square refers to the equivalent damping constant, that is C equivalent, while the term Ka square refers to the equivalent stiffness, that is K equivalent. Now in the second step, we will find out the damped frequency of the given system as required in the question. Since we know that for a single degree of freedom damped vibration system, the damped frequency, that is omega d, is equal to omega n into under root 1 minus zeta square, where omega n is the natural frequency of the system and it is always higher than the damped frequency, while zeta is the damping ratio. Since we know that omega n, that is natural frequency, is equal to under root k upon m, so for the given system for which we have already developed the equation of motion, we can write down the coefficients of the stiffness and the mass in this formula of natural frequency as follows: omega n is equal to under root k equivalent upon J naught, or omega n is equal to under root Ka square divided by 1 upon 3 ml square, or omega n is equal to A upon L under root 3K upon M. Also, zeta is equal to C upon Cc, where zeta is the damping ratio, C is the damping constant, and Cc is the critical damping constant. By substituting C equivalent in place of C in this equation, we get zeta is equal to C equivalent upon Cc. Since we also know that critical damping constant, that is Cc, is given by 2 under root J naught into K equivalent, or Cc is equal to 2 under root 1 upon 3 ml square Ka square. Also, Cc is equal to 2La under root Mk upon 3. So this is the value of critical damping constant Cc. Next we have C equivalent, which is the equivalent damping, which we find out in the previous step in the equation of motion for the system, as C equivalent is equal to Cl square. Finally, by substituting all these values in the formula of zeta is equal to C upon Cc, we get zeta is equal to Cl square upon 2La under root Mk upon 3, or zeta is equal to Cl upon 2A under root Mk upon 3. By substituting this value of zeta in the formula of damped natural frequency, that is omega d, we get omega d is equal to A upon L under root 3k upon m multiplied by under root 1 minus c square L square upon 4a square into mk upon 3, or omega d is equal to under root 3k square upon ml square minus 9c square upon 4m square. So this is the final value of the damped frequency for the given system. And with that, this problem ends here. Next we have another problem, which is problem 2.1 from SS Rao 5th edition, and it states that an industrial press is mounted on a rubber pad to isolate it from its foundation. If the rubber pad is compressed 5 mm by the weight of the press, find the natural frequency of the system and the time period. So first of all, we sketch our system by drawing a rubber block in between the foundation and the press. We can now express this sketch into a mathematical model by taking press as a mass or inertial element and rubber as a stiffness element as shown in figure. Next, we have formula of natural frequency omega, or omega n, which is equal to under root k upon m. So in order to find out the natural frequency for the system, we have to interpret our system elements in the form of k and m. Since the press is falling under the action of gravity, therefore it has some weight, and weight is given by W is equal to mg. By taking the value of m from here, we get m is equal to W upon g. Also, the rubber pad is acting as the stiffness element, and for stiffness we have F is equal to kx. And by taking the value of k from here, we get k is equal to F upon x. Now substitute the values of m and k in the formula of natural frequency. We get omega n is equal to under root g upon x. So finally substitute the values of g and x in the formula. We get the natural frequency, which is equal to 44.271 radian per second. By taking the reciprocal of this natural frequency, the time period of the system is obtained, which is equal to 0.142 seconds. So that's the end of problem 2.1. Next we have problem 2.6 from SS Rao 5th edition, which states that the maximum velocity attained by the mass of a simple harmonic oscillator is 10 centimeter per second and the period of oscillation is 2 seconds. If the mass is released with an initial displacement of 2 centimeter, find part A the amplitude, part B the initial velocity, part C the maximum acceleration, and part D the phase angle. So the solution of this problem starts by first focusing on the term simple harmonic oscillator, which is mentioned in the question. And we know that for a simple harmonic motion, the displacement function is given by x is equal to a cos of omega n t minus phi, where x is the displacement, a is the amplitude, omega n is the natural frequency, and phi is the phase angle. By taking the time derivative of the above equation, we get minus a omega n sine of omega n t minus phi. So this time derivative gives the function of velocity. Again, by taking the time derivative of this velocity function, we get x double dot is equal to minus a omega n square into cos of omega n t minus phi. The third equation is the function of acceleration. Since for equation 2, which is a function of velocity, the maximum value of trigonometric function sine occurs at 1. Therefore, we get x dot max is equal to minus a omega n. Let's say call it equation 4. Since the time period for a simple harmonic oscillation is given by tau is equal to 2 pi upon omega n, or omega n is equal to 2 pi upon tau. From here we can calculate the natural frequency, that is omega n is equal to 2 into 3.142 divided by 2, and we have omega n is equal to 3.142 radian per second. Now substituting the value of natural frequency, that is omega n, in equation 4, we get the amplitude, which is equal to a is equal to x dot max upon omega n, or a is equal to 10 upon 3.142, or a is equal to 3.182 centimeters. Next, we will find out the initial velocity. For that purpose, we have to take the initial conditions. For example, initially at time t is equal to 0, the initial position or displacement x is equal to x naught. Therefore, equation 1 becomes x is equal to x naught is equal to a cos of minus phi, which is equal to a cos phi. Actually, equation 1 is the function of displacement. That's why we use it here in order to find out the initial velocity by applying the suitable initial conditions. Now we have a cos phi is equal to x naught, or cos phi is equal to x naught upon a. By substituting the value of x naught and a in this equation, we get cos phi is equal to 0.6285 and phi is equal to 51.057 degrees, or 0.8911 radians. Now for maximum acceleration, we use equation 3, which is the function of acceleration, and for maximum acceleration, the value of cos equals to 1. Therefore, we have x double dot max is equal to minus a omega n square. After substituting the values of a and omega n in this equation, we get x double dot max is equal to 31.413 centimeter per second square. So finally, the initial velocity can be calculated by applying the same procedure as we did in order to find out the phase angle. So for this step, we simply use the function of velocity, which is from equation 2, and apply the initial conditions. Then after substituting the values in the equation, we get the initial velocity is equal to 7.76 centimeter per second. So that's the end of problem 2.6. Next we have another problem whose statement is the time period of a damped free vibrating structure is estimated to be 1.25 seconds. Suppose that the overall stiffness and mass of the structure is 1 kilonewton per meter and 5 kg. Calculate the damping constant of this structure. So in the first step, we use the formula of time period, and from here we calculated the damped frequency. Since in the question we are provided with the damped time period, therefore the damped time period gives us the value of damped frequency. So from here the damped frequency is found to be omega d is equal to 5.026 radian per second. Also, we know that natural frequency, that is omega n, is given by omega n is equal to under root k upon m, as we are already provided with the values of stiffness and mass. Therefore, by substituting these values in the formula of natural frequency, therefore we get omega n is equal to 14.142 radians per second. Since in this question we are required to find the damping constant of the system, therefore we are using the formulae which are related to the damping constants in some way or the other. That's why in this step we are using the formula of damped frequency, which is equal to omega d is equal to omega n under root 1 minus zeta square, where zeta is the damping ratio. As in the previous steps, we have already calculated the damped frequency and natural frequency. So by substituting these values in the above formula, we get the value of zeta is equal to 0.934. Now at this point, when we have find out the value of damping ratio zeta, we can use the formula of damping ratio, which is zeta is equal to c upon cc, where c is the damping constant and cc is the critical damping constant. So after finding out the value of critical damping constant cc, we can now finally find out the value of damping constant c for the given system. Since critical damping constant Cc is equal to 2 under root mk, therefore after substituting the values of stiffness and mass in the formula, we get Cc is equal to 141.421 Newton second per meter. Finally, after substituting the value of Cc in the formula of zeta, which is the damping ratio, we get the value of damping constant, which is found to be 132.087 Newton second per meter.